So this one is classified alternative to practical acid, alkali, and salt topic. Today we'll solve question 11. A student investigated the reaction between aqueous sodium thiosulfate and two different solutions of potassium iodide. And the student labeled the solution as C and D. Two experiments were carried out. The first one, a burette was filled with a sodium thiosulfate. So the burette is filled with sodium thiosulfate. And initial burette reading was recorded. Using a measuring cylinder, a student transferred 20 cm cube of a solution C into a conical flask. So student took measuring cylinder, fill it with 20 cm cube of solution C, and then he transferred that into a conical flask. So in the conical flask, there is 20 cm cube of solution C. Then 10 cm cube of sulfuric acid is also added because this reaction can happen in acidic medium or acidic condition. That's why sulfuric acid is added here. And 1 gram of potassium iodide is also added to form a solution of iodine. As a result, it will form an iodine solution. The flask was swelled and the flask was swelled to mix the content in the flask. And in the burette, we were having sodium thiosulfate, which is Na2S2O3. That's a chemical formula of sodium thiosulfate. Are these solutions C and D? Solution C and D are not acidic or alkaline solution. Solution C, it's a salt solution, like potassium iodide. These are not. This is not an acid-base titration. There are two types of titrations are there. One is an acid-base titration. Another one is a redox titration. This is actually a redox titration in which when the oxidation number changes for the element, the color will also change. So this is a redox titration, not the acid base. Aqueous sodium thiosulfate was slowly added from a burette and swelled the mixture. When the content of the flask turned pale yellow, light yellow, then what we did, so we add a starch. What is the purpose of the starch? Starch is used as an indicator. Actually, starch, maybe in biology, you have studied that the test for to check the presence of
will change to blue black.
Yeah. To test the presence of starch, you add iodine and it will turn blue black. If iodine is present, it will be blue black. If there is no iodine solution, yeah, iodine solution is there to test. So if in the solution, if the iodine is present, it will give a blue black. But if iodine is not there, then it will turn to colorless. So was added, it turned blue black. Why it turned blue black? When we add a starch, it shows that iodine is present. But when we are adding a thiosulfate from the from the burette, then iodine is also, like, amount of iodine is decreasing. Eventually, no iodine is there, and the solution will turn colorless. Once the solution turned colorless, now we identify that all of the iodine is removed from the conical flask. So more aqueous sodium thiosulfate was added until the solution turned colorless and the final burette reading was recorded. So you can use screen annotation to complete the initial and the final burette readings and the difference as well. .3, 4.1, and how much is the difference? .34, right? So 34.2 is the difference. It means how much thiosulfate is used in the first experiment. We used 34.2 cm cube of thiosulfate in the first experiment. Then student repeat the experiment. The conical flask was emptied and rinsed with distilled water. Why rinsed with distilled water? To remove the content from the previous experiment. Then experiment 1 was repeated using a solution D instead of C. So only difference between the two experiments, like in the first experiment, student used solution C and now student is using solution D. So a burette, same thiosulfate is there. So, and in a conical flask, the only difference is the type of a solution in the conical flask. Same amount of solution is there, but the type is different. Like we are using a solution D of potassium iodide, and that is again 20 cm cube is used, and the burette is filled with sodium thiosulfate, and the same procedure is repeated. What is the initial burette reading, final burette reading, and the difference? Initial is 20.8. Initial is 3.7, final is 20.8. And how much is the difference? Difference between the two readings? 17.1. So it shows that we used 17.1 cm cube to react completely with solution D. By looking at these, by comparing the two experiments, which solution is more concentrated? Is it solution C or solution D?
Solution C, because it requires more volume of
Sodium
thiosulfate.
Yeah, good. So that's right. Solution C is more concentrated because it required a greater volume for a complete reaction. And you can also compare the concentrations as well. Can you compare the concentration of C with D? Like here we need 17.1 cm cube for a reaction. Here we need 34.2 cm cube for a reaction.
We will take a ratio and then reverse it.
Yeah. So ratio of the volume is 1:2. Like we need twice amount of sodium thiosulfate in experiment 2 as in reacting with C as compared to reacting with D. So what it shows that C is twice concentrated, or C is having double particles as compared to D. Yeah, 1:2 is because look, the concentration ratio, the volume ratio is 1:2. The ratio of the volume is 1:2. Like in this, or you can also say 2:1 here for experiment 1, the volume needed is twice as compared to experiment 2. So means the concentration in experiment 1 was twice as compared to experiment 2. That also you can mention. So which solution of a potassium iodide, C or D, is more concentrated, and explain your answer. So which solution is more concentrated? So we'll mention C is more concentrated. And why C is more concentrated? What will be the reason? We'll mention because it requires
more volume of thiosulfate relatively.
And reason is that it requires greater volume of sodium thiosulfate for a complete reaction. Then how many times more concentrated is the solution of potassium iodide? Like when we are comparing C with D, so C required 34.2 cm cube and D required only 17. So it means C has a double concentration. Like example, the number of the particles, say in C were 20, but in D it will be 10. That's why they need a different. How to work out the ratio? If you check for this one, we need 34.2. For C, reacting with C, we need 34.2 cm cube for a reaction. And for reaction with D, we need 17.1 cm cube. So how to take a simplest ratio? To take a simplest ratio, you divide by the smallest value. The smallest value is 17.1 here. This is also 17.1. So what is the answer here? This will be 2 and this will be 1. So it shows that C is having double concentration because it required double volume. So you can mention because experiment one, C was experiment one and D was experiment two. So ratio you will mention for experiment one to experiment two is to one. If you mention one is to two, then it will be wrong. Why? Because then the ratio will be different. The ratio of experiment one to experiment two is to one. That's why. So how many times it is more concentrated? So you will mention it twice or two times. Predict the volume of a sodium thiosulfate that would be needed to react completely with 30 cm cube of solution D. Look, if we were having 20 cm cube of solution D, how much thiosulfate was needed from a burette? We need 17.1. So if we have 30 cm cube of solution D, how much thiosulfate is needed for a complete reaction X? So what we do, we just cross multiply. Like 20 required 17.1, so 30 cm cube required X. What's the answer for this? So 25.65 cm cube. Even you can write, because the burette is accurate to 0.1 cm cube. So you can write here 25.6 because burette can measure, the smallest value it can measure is 0.1 centimeter cube. This is right, but with reference to the burette, we need like 25.6 as we round it off. And one mark is for writing the unit. Yeah, unit you have to mention as well. It's important that you mention or write the unit, taking a ratio and writing the unit. State two sources of error in this experiment and two improvements. Whenever a question is there regarding the sources of error and improvement, you should always go back to the first part of the question where they write everything about the question. Because that point you can find the errors there. Okay, by reading this instruction, can you identify the error?
Measuring cylinder was used to fill 20 centimeter cube of solution C.
Yeah, so measuring cylinder is used
We
for
can
that.
use burette.
So we can use burette for that, but you cannot mention pipette because it is not 25 cm cube. Parallax error, actually, in these experiments, parallax error in physics, if you mention about parallax error, that's fine. But for chemistry, usually parallax error is not even, rarely you will find an option. Even I don't remember I have seen a parallax error mentioned in chemistry errors. So usually it's about the type of apparatus used or the technique used.
They
As
gave us the diagrams to
yeah,
record the reading, so it does not count as parallax error.
yeah, that's my point, that parallax error does not score a mark here. Then what you should do for titration experiment, what is another error is the reputation. Like when you're,
Overshooting endpoint.
yeah, overshooting an endpoint, that is an error. Carrying out experiment only single time, that is an error. Use of the measuring cylinder rather than a burette or a pipette, these are the errors. Identification of the color, actually it will cover in a overshooting at the endpoint. Like if you mention student did not recognize the color change promptly, that is counted as overshooting or going past the endpoint. So whenever titration experiments are there, the errors, remember, like type of apparatus used, the technique you use. Like example, if you did not repeat, then this is also an error. Because maybe when we did this experiment and we got the value like 30, the difference was 34.2, but that was done only once. It should be done twice or thrice until we have a concordant result. So two sources of errors in this experiment: the use of a measuring cylinder, then going past the endpoint, overshooting at the endpoint, or did not recognize the color change. And the other one, as we mentioned, Because in these experiments, what we usually happen when we are carrying out a titration, so burette, we open the tap. So that what might happen, instead of adding drop by drop, when the color is getting like lighter, paler, the student just open the tap for a longer period of a time. So that will be overshooting. If we say colorimeter for movement or
We don't need colorimeter, it
no,
is
no,
very visible change.
colorimeter is not a colorimeter. Actually, if the question was about identifying the rate or the speed of a reaction, in that case you can mention, but not in a titration. So how to overcome this overshooting? Just mention
Add
add
slowly.
slowly or add drop by drop near the endpoint. That's it. That's how we overcome this. So two improvements: use burette. Why I cannot mention pipette here? Because the volume was 20 cm cube. Yeah, one of the improvement is use of burette, and what else is there? So we should repeat and one of the error here, we did not repeat the experiment, so we should repeat the experiment. And other thing, add small quantity or drop by drop near the end point. Yeah, repeat and take the mean or average is also another one.